Hello, my name is Alan Rose, and this is a presentation I delivered at the Automotive Corrosion Symposium in Detroit, 1st of April. So I'm going to talk about using computational corrosion analysis to deploy corrosion prevention and control in automotive design. So this is based on the work that we've done at Cordesa in the aerospace and defense sector, and the aim of this presentation is to hopefully highlight some findings and useful tools and approaches that the folks here at the Automotive Corrosion Symposium can adopt in their practices if they're relevant to automotive design. So the agenda is I'll just quickly introduce Cordesa and what are the key drivers and challenges. Why am I bothered? Why is corrosion assessment important, particularly the potential of deploying computational corrosion analysis. So I'll present a workflow that we've developed in our aerospace and defense area that I think is a good starting point for automotive designers. What can we learn from this workflow that we've developed? And I'll point out a couple of standards in the military side that might be useful to folks in the automotive sector considering how they can extend this technology. And then the workflow itself is kind of like a 1D type of approach, get your arms around the problem, and then a deep dive using a very simple kind of GUI approach that materials and process engineers can quickly use. Or if you have the expertise and resources, you can import the full CAD of your system, and there are ways there of highlighting very quickly corrosion risk. So Cordesa, we're a small company. We're based in Tyrone, Georgia, which is about 20 minutes from Atlanta Airport. And here's a little bit of a background of some key players in this work at Cordesa, and you can get this presentation as a PDF and look at your leisure. But essentially, my background is computer-aided engineering, computational fluid dynamics. Keith, his background is expertise on the reduction of hazardous materials and deployment of new and alternative materials and processes that keep you on the right side of OSHA, EPA and REACH. And Dr. Sivaplani heads up our electrochemical laboratory. He's had a big hand in the development of protocols for measuring and characterizing the necessary data to enable corrosion simulation. So as a company, our mission is to help our clients quickly develop, qualify and implement corrosion resistant materials and the coating processes and application processes. So we use simulation tools to speed up this development process. So often I've heard, certainly in aerospace, it can take like 10 years plus to introduce a new material. Automotive, under higher pressure for getting out new models, it turns out that even in a 2-year program, there's not much time left for physical materials testing. So I'm going to present to you simulation techniques that can run in parallel with this design process to shorten the development process for material choice. So as a business, Cordesa, we develop software for material selection. I'll introduce our main software, Corrosion Gin. We've also do a lot of engineering services, and we've developed some techniques and workflows and simulation capability that we've used to develop our own hardware. For instance, we recently developed and deployed a hardware for mobile plating and anodizing of aerospace components. And we provide ad hoc services to some clients, guidance, consultancy, corrosion panel advisory boards, corrosion assessment and so on. So corrosion prevention, why am I bothered? Well, first of all, obviously, safety. We're all concerned about safety. But there's a few more bullet points here that I like to mention. In particular, that several studies have pointed to the benefit of having available better tools to improve design practices right from the get-go. Choices made very early on can impact sustainment and life costs of your products. The US Navy found that 40% of corrosion costs can be eliminated by better design. So, these tools up front are very important. We have stress analysis, thermal analysis, impact analysis, but very little is used of corrosion simulation tools. For the military, it's important that they obviously keep their platforms and planes out of the maintenance shop, and readiness is a key metric, and it was as low as 50% for FA-18, although they've improved that now. So another takeaway is, during the life, certainly on the aerospace components, you're talking like airframes, you're talking like several decades, okay? Maybe it's 10, 15 years for an automobile, but on the aerospace side, sustainment becomes a big thing. So you can choose some materials early on in your design, but when it comes around to maintenance, like several years down the road, those materials can actually end up being banned. So for instance, cadmium, awesome product for corrosion protection, has now been eliminated. So zinc nickel is a replacement coating. So how, after decades and decades of experience with other systems such as cadmium, how can we suddenly implement and deploy a new coating in a matter of a handful of years? It's very challenging, and computational simulation can help that process. Now then, I talk about, certainly on the automotive side, these large companies that design and collaborate with a large supply chain. There's a challenge of deployment. So here's an example of a client that we have that has stated that out of tens of thousands of the designers and engineers, product engineers, all of them can have a possible impact, positive or negative, on the durability and corrosion resistance of a system. And it turns out that maybe only 1,000 of them actually have materials and process experience, and maybe only 43 of that total number of designers actually have significant corrosion experience. So it's kind of like an inverted pyramid here. So what we need to do is provide the key information when and where it's required in the hands of the designers. Get expertise from the corrosion people upstream to the designers. And this is the workflow that we've developed at CoreData, and also that we are developing for a US Air Force funded program on C-17. So I'll take a few elements of this. So we're working with Siemens Digital Industries. Now they have the Team Center, the product life management software. So we're using that as the environment in which we have our corrosion gin software, we have 3D multi-physics capability with the CCM Plus software, and we have our data and tools completely within this environment. Now many companies have this Team Center. In fact, US Air Force, their PLM software has to be Team Center. It's been chosen as the PLM software. So we have all these tools in that same environment, and I'll go through this kind of stepwise process from a kind of a 1D corrosion gin analysis through to the deep dive 3D analysis to get your corrosion rate map on your complex components. Before I do that, I want to take a step back. I mentioned there's some military standards. I can imagine there would be similar best practice guidelines in the automotive world. But let's take a look at two in particular that I'm concerned with. It's difficult to see these, but in the PDF you can zoom in. So on the left-hand side, we have a materials and processes corrosion prevention standard for aerospace weapon systems. That's 1568. And then over on the right hand side there's one in particular for galvanic compatibility. Now then, I shall pull out a couple of clauses, as it were, from the military standard 1568D. So there's a piece in there and it uses shall be language. Okay, so modeling and validation testing shall be performed to identify corrosion prone locations. So this is very interesting because if you're building and designing a system and you have to do at some point some physical tests, how do you figure out what surrogate models, what specimens to create if you don't know where the corrosion is going to be? Now, a lot of folks will go, well, we've been building these for years, we know where the corrosion is going to be. But like they say in the stock market, past performance is no prediction or guarantee of future performance, and sometimes it's difficult to extrapolate. So with computational modeling, there are methods to look at your system, do that kind of a technical audit, and highlight corrosion prone locations, and I'll show you. And then once you've done that, you can start considering physical testing, where you include the actual materials of assembly, the techniques, and the corrosion protection schemes that you want to use, and you can build and physically test those systems. Also within this 1568 standard, it actually calls out other standards. One of them is for dissimilar materials, Mil Standard 889, which is this other one over here. Now, that has been recently revised, and it's having quite an impact in aerospace and defense, because the way of calculating galvanic corrosion risk has been completely changed, and we'll kind of dig into this in a little moment. No longer do we use galvanic potential tables. You actually have to calculate the galvanic corrosion current, and that's done by applying what's called mixed potential theory, and this requires more data, polarization curves. So we'll talk about that in a moment. And it's more accurate, it's more reflective of kinetics. So we're going into a little bit of detail here on why did they change the Mil Standard 889 from potential tables to this calculation of galvanic corrosion current. So briefly, what we have here is a potential table of materials, alloys, elements, materials, and along the horizontal axis we have the open circuit potentials, and the more negative, essentially, the more active the material, the more positive, the more noble. So in a scenario, for instance, where in maintenance they use stainless steel fasteners, and if you look at the Mil Standard, the old Mil Standard, it would suggest that that's a good choice, because the potential difference between your stainless steel fasteners you intend to fix and an aluminum structure is smaller than the potential difference between, say, titanium and the aluminum structure. But in practice, this wasn't found to be the case. So some experiments are done, and if you produce specimen couples of stainless steel and aluminum and titanium and aluminum, you would find that the galvanic current between them, which is proportional to the corrosion rate, is actually higher for the stainless steel aluminum couple, right at that point where you're around about 3.5% sodium chloride, which is kind of like the seawater concentration of salt. So this isn't a good thing, because your standard points you towards a material that is not going to be the best choice. And as I said, they found this in practice with some tests. We've got some aluminum alloy here, and you can see titanium fasteners, stainless steel fasteners, and the corrosion, the galvanic corrosion, is much, much worse around the stainless steel fasteners. And if you have the polarization curves of these materials, the aluminum, titanium, stainless steel, you can actually predict this up front. So I'll show you how we do that. So you can see the higher corrosion around the stainless steel fasteners. Okay, so this military standard 889 is now D for Delta. And the first thing I notice is the change is not dissimilar metals anymore. It's actually galvanic compatibility of electrically conductive materials. So this is going to capture a much wider community. It's not just, like I said, the metals anymore, but it's if you have, you've got alloys, you've got composites that have, maybe carbon fiber in there. You've got conductive gaskets, sealants and gap fillers and all sorts of treatments that may have an element of conductivity. They now come under this standard. It's important. So if you look in the standard and it's available, you just do a search. We have it on our website at cordesa.com as well. The things I would point out is they no longer use a potential difference in this revision D. They actually calculate the corrosion rate of the anodic member of that couple using mixed potential theory, and that is from the crossing points of the respective polarization curves. So, okay, how do you get the data? How do you get these polarization curves? Because one person could gather the data and it could be quite different to another person depending on their techniques and equipment. So in the same standard there's an appendix, and Cordesa were involved in a round robin which was testing this recipe, this protocol for gathering this data, and it's quite robust. So essentially now it's outlined in the appendix on how to gather that data, and we have folks at Cordesa that can help you do that. So now that we have this procedure, there's also some post-processing that has a few nuances about deconvolution. Then you cross the curves and you can get the corrosion standard. The corrosion rate. And I see this as a living standard because when you think about it, as soon as a standard is printed, it's kind of almost out of date because new materials and coatings are continuously being introduced. So now with a new coating, you can follow the standard and comply and gather that data in that compliant way and then follow the standard to look at the corrosion issues. So back to our corrosion workflow. So first of all, to get your arms around the problem, you might want to do some trade studies, look at the selection of coatings to see whether there's some risk up front. So we use corrosion-prone. This is already commercial software that's been out a number of years in the cloud, or you can have it installed on your own IT infrastructure. Now it's incorporated into Teamcenter. So I can do a quick demo, but it's available in the cloud, and you can contact me if you want to kind of evaluate it. So here we have a little video showing how you can very quickly use corrosion-prone. So we describe our materials. Well, our environment is mill standard 889 data, and we have substrate, designation, coating, and treatment. So the substrate could be the metal, alloy element, and then we have different series. We also have different tempers, and then a coating and a final treatment. So let's look at the scenario of the stainless steel fastener, 15.5 pH. It's a click, and then we can see out of that couple which is anodic, the aluminum, which is cathodic, and the table summarizes the galvanic corrosion rate in absolute microns a year, mils a year, or in the ranking that's actually in the standard. So we can very quickly create another group. It automatically populates these materials, and we can swap out stainless steel for titanium, and it's just a click. It pulls the polarization curves, and now you see it's titanium, it is cathodic, but we've managed to get the corrosion rate way down just by a better choice of materials. Another way of protecting, avoiding galvanic corrosion is maybe a sacrificial coating of the fastener. So let's consider a coating of not cadmium. We'll use the more environmental friendly zinc nickel, LHE, low hydrogen embrittlement, and it's click. And now you can see that aluminum is cathodic because you're actually cathodically protecting the aluminum with the zinc nickel. So the corrosion rate is a corrosion rate of the zinc nickel, which also gives you an indication of how likely that is going to last, how long it will take to consume it. So that was pretty quick, but here's a summary table. What I did was consider several groups, 3 groups, material 1, material 2. So I chose aluminum 7050, and with group 1, group 2, I looked at stainless steel, Ti64, and I managed to get my corrosion rate down from 271 at the interface to 3.5 microns a year. And then I showed how you could choose zinc nickel, and that corrosion rate is actually the corrosion rate of the protective coating. Aluminum 7050 doesn't corrode in that couple. So that was very quick. You can go straight to the standard, do exactly the same. For folks that are old enough like me, you might remember mileage charts before GPS, distance between Dayton, Ohio and Atlanta, and you just kind of look along between two cities, and the intersection gives you the distance. What we have here is our 16, 23 and 31 are the numbers, identifiers of these materials of aluminum 7050, the Ti64 and the stainless steel. And what we do is just run our line straight across the aluminum and then drop 2 lines from the Ti64 and the pH 15.5, and you can see these corrosion rates here are rankings, and the ranking is over here on the right hand side. Beware, it's not kind of uniform and consistent. We have 0.01 to 0.09 mils a year, then 0.1 to 0.9, but ranking 3 is 1 to 5 mils a year, so watch out for that. But when we use corrosion gin, it tells you what the actual corrosion rate is. All these numbers are positive, so what is corroding what? There's another table. It does give you a warning. Do not use this for determination of compatibility. It's just to help you get the sense correct in terms of what is anodic and what's cathodic, and the activity is stacked up in this table for each of these materials. Okay, so the assumption there, and it says in the tables, the assumption is anode cathode area ratio equals 1. That's not always the case. You want to do something a bit more accurate where you take into account the data. Then we have a GUI. We've introduced a GUI with several different geometries. In aerospace systems, we have bonded joints, fixtured joints, bushings, and common geometries that you can put into families. And we've automated the creation of those models. So with a GUI, we can look at these different options in the family. And then we have a GUI and we just pop in the numbers. So a materials process engineer can run the GUI on the left hand side, and they don't have to create a computational mesh on the right. That's done automatically. They simply get a report of the corrosion rate of this fixture system, or in this case a bushing. Very quick. And now you've not got this constraint of a 1-to-1 anode to cathode area ratio. Or indeed, you can also do different electrolyte thicknesses. If you have resources, you have CCM Plus already, and folks that know how to use that, they can just import the whole CAD, like in the top right hand corner here, and do an analysis straight on the explicit CAD file. We did this for a piece in this leading edge flap actuation system for the FA18. Very complex. You got lots of components adjacent to each other, lots of different coatings, and the workflow is just similar to like a thermal analysis or stress analysis. You bring in the geometry. You hopefully have the 3D. If it's very old, we've had to build 3D models from 2D PDFs or laser scan. Either way, you need a 3D digital model. You assign your materials under the hood. That pulls the required boundary conditions, the electrochemical data, the polarization curves. You mesh your problem, this bushing and this lug, for instance, and then you get your output. And depending on whether the electrolyte is kind of a thick bulk electrolyte or a thin layer, you can get different answers. So you can get polarization curves for different thicknesses. This is something that we do at Quadesa, or we have a method for deconvoluting as well. And what this shows is the intersection point for the electrolyte with the stainless steel and aluminum couple, whether it's bulk or electrolyte, or a thin electrolyte. In thin, you get a much higher current density, which is proportional to corrosion rate. because of the higher oxygen diffusion. There's much more aggressive kinetics, so that can be accounted for. So then you can apply your bulk data or your thin layer data, and in thin layer data on the right hand side you can see this high intense localized corrosion around the interface of that bushing, but much higher. Okay, so the 3D corrosion analysis toolbox. So I'm going to pull all this together now. So essentially, whether it's 1D or templated 3D or a full 3D, you need the fuel for the solver engine. You need the electrochemical database, and that's something that we've built up. We have a lot of aerospace materials, automotive materials. It's just a matter of making that investment and gathering, agreeing a protocol. We can learn a lot from that mill standard, gather that automotive data, and then we could have an electrochemical database for automotive materials. Now then, I didn't go into this aspect on this Air Force program, but it's clearly relevant to automotive sector as well. We have a methodology for taking these deterministic corrosion rate calculations and applying factors to them to take into account the actual life of an airplane, its mission profile. So just as you buy cars, and you may have a car in Nevada, or you may have a car in Michigan, or by the seacoast in Florida, entirely different environments. With that knowledge of those environments, you can splice that data in, and you can get the fidelity between my C-17 aircraft that's in Guam or my C-17 aircraft that's in drier climates. So with these databases, we can, if we're in design, OEM design, then we can just bring in the full 3D CAD, and at the push of a button, we can now automate the application of that mill standard 1568D, where we find the corrosion-prone locations. We run it through the 3D CAD. So just as I did like 2 or 3 material couples in my gin demo, that is now done for each and every interface, fastener, washer, nut, bolt within this whole system, done automatically. I mean, it's on a computer, so it's no problem. It's done fast. And that will give you your potential areas of high corrosion rate. Maybe it's because of bad or poor material choices. Remember, these systems are built by, thousands of designers. So there's so much kind of opportunity for mistakes to be made. Or just coatings just simply left out. So this will check for like kind of emissions and errors, and also for physically bad compatibility between some coatings. Now then, if we had this up front, we might have been able to spot this issue where on the top of the wing here, these yellow dots are actually kind of corrosion issues due to material choices on these fuel ports. So this in sustainment, this has been seen by the Air Force. And what we have now with this tool, our materials and process engineers can choose one of the out of the family of options. This is kind of like some kind of fixture system or a bushing system. Choose the materials very quickly without CAD experience, get themselves a corrosion map, and then swap out material choices or some dimensions and make some informed choices on what to do to mitigate and eliminate that corrosion. If you have expertise on hand and the resources, then you just pull the 3D CAD itself. Your computer-aided engineering analysts pick it up, run the cases, and predict the corrosion, and then iterate on what might be better choices. Okay, so to conclude, computational corrosion analysis can significantly compress the vehicle design process. It informs upfront material selection. It can point out any errors and emissions as well, and I think will contribute to this goal of virtual vehicle validation, where you can do a lot of work upfront computationally. People call it digital twin or digital thread. you connect that material data to what you expect will happen in the field. So I presented a workflow of analysis tools that Cordesa have developed and used in our aerospace and defense work. I think there's a lot there that can be used and exploited by the automotive community. We saw how at that higher level, those tens of thousands of CAD operators can be provided with the tools to do whole system analysis to check for material incompatibilities. Any kind of problems that are highlighted, we can do a bit more of a deep dive very easily with these families of geometries and fixture systems where materials and process engineering experts can do a 3D analysis with the use of the graphical user interface inside of Teamcenter. If you have the experts that can use the CCM Plus from the get-go, they can pull in the 3D CAD and do the same. So from aerospace and defense, we've learned that a couple of MIL standards, 1568D requires identification of corrosion-prone locations. So like I said, that can be done by the push-button approach that I just showed earlier. 889D is actually a new methodology. It's interesting to take that on board because potential tables can lead you to bad decisions. And a lot of effort and investment has been made by the defense community. The standard has took a while to come out, all the data behind it as well. But it's aerospace data. So, Cordesa have the capability to do the same and measure data relevant to the automotive community, and we can do something similar. This work does demand polarization curves, and the protocols are available. So at that point, if you have any questions, feel free to email me here, and I hope you found this useful. Thank you very much.